Sir, one more thing. Can you please share this PPT with us? Please, as a
Ah,
reference.
I'll do that.
Thanks.
Um, so, um, right. So where we were was we derived um, the uh, the the derived sort of empirical formula um, for the minimum impeller. So this is right now. This is equation 818 of Duran. This is the minimum. This is the minimum impeller uh, RPM, whatever, rotation speed, velocity, the terms in the book. This is the minimum impeller velocity required for, um, I think they use the word JS for just suspending the solids. And this I went through in the class last time. I basically said that there is a dimensionless term S, which is a function of the impeller type, and the dimensions. So it's a function of the type and the dimensions of the impeller. And then the rest of it, except for the di to the power 0.85, reflects the properties of the suspension, the kinematic viscosity, the fraction of solids, the particle size, and this G times rho P over rho L minus 1 is a measure of the gravity, the net, the net, the net gravitational force on the. I shouldn't say actually I wrote buoyancy, but this is actually, uh, there's a downward weight, and then there is a upward force due to buoyancy. So it should probably be written as net. Uh, this is the net force, the net downward force. And then we look at an example. So it should be emphasized that this is only for ungassed systems, right? There is no gas going through the reactor. And we were at the point where, we just started discussing what we do in gas systems. So turning to the um, example, um, where the hell is it? This is so returning to the example which I covered in the class. Um, um, I just want to point out that so here is the formula. This is the formula, and this is the dimensionless constant S, which is given by table 8.4 over here. So if you know the impeller type, which in this case, for example, in the problem we did the Rushton impeller with di over dt equal to 0.5 and ci over dt equal to 0.25, then the value of S is 4.25. And I also mentioned to you that if you want to extrapolate between those values, then you can use formula 819. if you don't have the exact values, you can interpolate using this particular formula. And this was the example that we did, and the number that we got was a very small number. It's 18.6 RPM. This is not a whole lot, so you need very little to just keep the solid suspended. And as Duran points out, the reason for this is actually this is a major phenomenon in chemical engineering reactors that are used in, for instance, the mining industry where they have very heavy particles. But in our case, if you're dealing with cells, this term over here, um, this term over here, which I referred to as the net downward force, is really, really small because rho sub p, which refers to the density of the particles, in this case we have cells. The density of the cells is actually only marginally more than that of the liquid. So normally rho sub p is on the order of 1.05, 1.10 grams per centimeter cube, and rho L, which is the density of water, is 1.00 grams per centimeter cube. So because of the very small difference, the net downward force on the particles is very, very small. There's very little pulling the particles downward, and therefore they don't have any natural tendency to settle. You need very little impeller speed to keep the particles in suspension. So this actually, in practice, turns out to be not very important. So that's what she's saying. Uh, the last line, she says, complete suspension of cells and small cell clumps is generally achieved at low to moderate stirrer speeds. This is mainly due to the small size and almost neutral density. The density is close to that of the suspending liquid. Um, of course, if the particles become really, really, you know, big in size, then the picture changes quite substantially. Okay. Um, we were now next. We reached basically. We started covering how do you modify this formula when you have gas flowing through the reactor. And the key point here is that, um, roughly speaking, when you pass gas through a liquid phase, and we have already seen what are the gas distribution profiles. Uh, what we did not discuss at length, but it is discussed in the book, is that as you increase the gas flow rate, um, gas starts to accumulate behind the impeller. By behind, I mean um, um, if so there is a surface that is pushing against the water, right? So take the example of the Rushton impeller. The front of the impeller is pushing on the liquid. It turns out that at the back of that impeller, gas starts to collect, and it forms large clusters, because of which uh, the the impeller is not able to move very efficiently. So there is a drop in the ability of the impeller to deliver power to the liquid. It's called, this is what she mentions here, if fall in power with gassing. So I mean, as you increase the gas flow rate, the impeller becomes less and less efficient in delivering power to the liquid, and therefore you need to compensate for this, you need to turn the impeller at a faster rate. And these two formulas, 820 and 821, these are giving you basically the formulas you need to adjust for it. And the main thing you need to know here, these are actually very, very special formulas, so they're hardly likely to be of much use. So notice, first of all, that they apply only to Rushton turbines of two very special sizes. Di over dt equal to point. This is one third the size and half the one third the tank diameter. The impeller diameter is either one third of the tank diameter or half of the tank diameter. And in these two cases, to the NJS, this first term here is the NJS that you calculate for ungassed systems. And having calculated it for ungassed systems, you add to it an extra term that depends upon this quantity called FGV. And this FGV is also known in the jargon as VVM. And actually, this is, sorry, uh, it is called VVM, also called VVM. And it is nothing but the gas flow rate divided by the volume of the liquid. Now, since the numerator, so this is in liters per minute, which is the gas flow rate um, in liters per minute, divided by liters of reactor. So this has units of 1/minute. So FGV is volume of gas delivered, the rate of gas delivery per unit volume of the reactor. And typical numbers, for example, if you operate a reactor in the lab, it is often operated at around half to 1 VVM. So, for example, if you have a reactor in which the volume of the liquid is, say, 1 liter, 1 VVM would mean that you would be delivering the gas at 1 liter per minute. And this formula is basically saying take the NJS that you calculated for the ungassed system, and to that you add an extra term which increases with, roughly speaking, the gas flow rate through the system, measured in VVM. So it's a kind of a weird formula. The only thing you have to remember is this quantity isn't 1 per second, so RPMs per second, this NJS, whereas this FGV is calculated in 1 per minute. So this is a really weird formula where you have to keep track of what the dimensions are, and that's about it. I mean, it's just an empirical formula that you need to know, compensating for the fact that when the impeller starts to operate in a gas system, its ability to deliver power to the liquid drops. I think this is discussed. If you want to see a little bit more about what is happening here, it is, let me see if I can, oh, here it is. Um, oh, here it is. So this is showing you what is happening behind the blade as the impeller turns. So, weird kinds of gas structures develop behind the blade. So if you see over here, this is the top figure is showing you that as you increase the gas speed, so keep, for instance, the impeller speed constant, and if you start increasing the gas flow rate, then the top figure is showing you the kinds of gas structures that form behind the blade. For example, the first picture is showing you that vortex cavities form. So this is shown in more detail over here. You can see that at the back of the blade, this is the back meaning behind the direction of rotation, these structures that are forming, these are called vortex cavities. And as you increase the gas flow rate, instead of these vortex cavities, what develops is what is called clinging cavities and then large cavities. And when these large cavities develop, large chunks of gas trailing behind the blade, then the power delivery, the ability of the impeller to deliver power goes down. So I should point out that actually much of this work is empirical. The reason being that these are very complex. Uh, these gas flow patterns are so complicated that you can't really model them. And in any case, the phenomenon of turbulence is one of those areas that has never been understood and still remains just an as important as it is just an empirical area. There's no overarching theory for turbulence. It's all sort of empirical and statistical. So, having done that, we move now to the next topic. Well, we want to move towards the um, mixing of liquids. So we've already covered how to make sure the gas is well mixed. We've also already done how to make sure the solids are well mixed. And now we are moving on to how to keep the liquid itself well mixed. And before we move on to that topic, so actually, roughly speaking, we already know. So let's move on to the next topic is this is the third major topic, which is mixing of the liquid phase. Uh, this is where we want to go, but we have to make a slight detour. Um, the reason being that it turns out that good mixing of the liquid basically requires that you put a lot of power into the impeller. It's basically a methodology that says that if you have enough power being delivered to the impeller, your mixing will be good. So, as a prelude, but as a prelude, before we can do this, as a prelude, we need to discuss the topic here is um, the question of power. And so the topic we want to discuss is estimation of power uh, required for stirring the liquid. Okay. Um, Now, uh, this how much power you need to to stir the liquid kind of depends on what kind of forces you need to overcome. And as I think I already told you, there are two kinds of forces. There are two kinds, majorly, two kinds of major forces um, in 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 a reactor. So the first is viscous forces, and the second is what is called inertial forces. And these are the forces that result from momentum transfer by diffusion, which I will elaborate in a minute. And these are the forces that result from momentum transfer by convection. And as you'll see, once you know which is the dominant mode of momentum transfer, you know what kind of forces you have. Once you know what kind of forces you have, then you can estimate what kind of power you need. So, the first point is to sort of roughly understand. Um, Now, I should also add here that these viscous forces are uh, dominant if you have laminar flow, and inertial forces are dominant if you have turbulent flow. And to understand this, so first of all, let's just understand how there is momentum transfer by diffusion, by a sort of an intuitive argument. So this is momentum transfer by diffusion. And you've probably seen this, but my main point here is that so this is typically observed, as I told you, when you have laminar flow. And the physics immediately shows that the transfer in this case has to be by diffusion. To see this, consider a stationary plate. And on this stationary plate, you allow a film of liquid to move, let's say, to the right. So this is a film of liquid moving, moving film of liquid to the right. So you know from this must have been repeated many times that the velocity profile that develops in such a place, you have no velocity at the boundary because the plate itself, so this plate itself, this is a stationary plate. Since the plate itself is stationary, there is no slip at the boundary, which means the velocity at the interface is equal to zero, and then the velocity increases until you go to the free surface and you end up with a velocity profile that is essentially linear, like that. Now, in such a system, essentially what is happening is the flow is taking place in layers. You can imagine, thin layers sliding across each other, and essentially the molecules in the top layer are moving faster than the molecules in the second layer, which are moving still faster than the molecules in the third layer, so on and so forth, until in the last layer, the molecules are barely moving. And essentially, the molecules in the top layer that are moving very fast, when they diffuse downward into the second layer, their high x momentum is transferred into the second layer. And likewise, the high velocity molecules in the second layer, which are moving faster than those in the third layer, when they move to the third layer, they transfer their momentum. So this is how momentum is transferred in the y. So if I call this the x direction and this is the y direction, so notice that we are talking about the transfer of momentum in the x direction. So this is x momentum, right? This is velocity in the x direction. This is the momentum of the molecules that are moving in the x direction. So the momentum is in the x direction, but it is being transferred in the y direction. So the point I'm trying to make is, in this case, so one can see that the two major points are: one, there is no bulk, bulk or convective flow in the y direction. There is no movement. The entire flow is taking place in the y direction, in the x direction, right? All the particles are moving in the x direction, and yet there is a transfer of momentum in the x direction. So stated differently, you are getting a momentum flux in a direction, right? Namely, the y direction, even though there is no bulk flow in that direction. That means this transfer of momentum is taking place by some mechanism other than convection, that is diffusion, which is what I just described to you. That basically, from the layer where the molecules have higher velocity, from those layers, the molecules, they diffuse downward into the second layer and help accelerate their movement. And then those molecules in the second layer, they're diffusing to the third layer, and so on and so forth. So in this layered motion, diffusion is the main mechanism of transfer of momentum, because as you can see in this example clearly, there is no bulk flow that is helping the transfer of momentum from one region to the other. So this is basically an example of diffusion as mechanism of momentum transfer. But the moment you start, violently moving the liquid. So, for example, even in this case, if the pressure drop were huge and the liquid started to move at extremely rapid rates, the layered structure disappears, and you have little tiny packets of liquid being thrown from, for example, the upper layer to the lower layer, and from the lower layer to the upper layer. So these are literally packets of liquid which are executing bulk movement. It's not diffusion. It is literally transfer of the packet from of a small liquid particle or a liquid packet from one region to the other. And in that case, what you have is momentum transfer by convection. And this characteristic is observed in turbulent flow. So I'm pretty sure you've done this stuff in your chemical engineering courses, but here momentum is transferred by bulk movement of liquid packets, liquid um, packets, which in the jargon are actually called eddies. They use the word eddies to describe these little packets that are moving around, i.e., um, by convection. So in reality, of course, you know, you don't have a one or the other. It's just that one is dominant and one is small. Both mechanisms are operational, and one is small compared to the other. And the way to decide which one you have is actually was determined sometime in the 19th century by this guy called Reynolds. So the next question is uh, how to decide which mode of momentum transfer is dominant, and which one can be neglected. Which one can be neglected? So you've already seen this. I suspect. Is it fair to say that you've already seen this in pipe flow and flow across solids?
Yes, sir.
So essentially, all that changes is uh, the definition of uh, the Reynolds number. This depends upon the system you're dealing with. So, for example, uh, the Reynolds number tells tells us uh, this information. So uh, in pipe flow, so the Reynolds number in pipe flow is, D is the diameter of the pipe, and then U is the, I should use the same notation. So V is the average velocity of the liquid, uh, rho divided by mu. But if you have a different system, then you have to define a different Reynolds number using the appropriate diameter, the appropriate velocity, and of course, rho and mu remain the same. So, in the case of stirred reactors, what they define is what is called we define what is called the impeller Reynolds number. And this is denoted REI. And this is defined as, so we'll start from the basics. So the Reynolds number is actually, and that'll give you also some insight into why the Reynolds number for pipe flow is defined that way. It is defined as, the main thing you need to know is that it is actually the ratio of the inertial forces or inertial stresses divided by the stresses that result from viscous effects. So it's basically stresses resulting from convective flow divided by stresses resulting from the diffusive mechanism. Okay, and inertial forces. If you go back and take a look at Bernoulli's law, this should become the magnitude of the inertial forces has the order rho multiplied by vi squared. So in our case, we are using the impeller tip speed. So keep in mind. So always, the moment you see inertial forces, this rho vi squared is a measure of the inertial stress. This has units of force per unit area. And actually, you could do it without multiplying it by the area, as I always do. The only reason why I do it is to convert this into forces. Rho vi squared has the units of stress. So this is the stress that results from convection. And the viscous forces, if you remember, you always define something of the form dv dx. So it is, for instance, dvy. In our case, for example, in the previous example, you can say that the stress is, in the example we just took a look at, this one over here, you have essentially your stress will be mu times partial of Vx with respect to y. This is the viscous stress that results from the layered flow. So if you keep this formula in your mind, then an order of magnitude of the stress is going to be mu multiplied by Vi divided by the length scale representative, which is, so here, this is a measure of the viscous stress, and rho Vi squared is a measure of the So this is a measure of the inertial stress. This is the stress that is resulting from um, this is inertial stress. And you can see that if you know, this di squared, I have simply added for converting the stresses into forces. You need not have added it because ultimately we cancel them anyway. So cancel these out, and basically what you get is this has to be equal to rho multiplied by vi, because the vi at the bottom cancels out with the vi squared at the top, and then you get the di at the top, and you get then the mu. Now, this is the same argument that is used to derive the Reynolds number for pipe flow, except that the velocity you use is the mean velocity of the liquid, and d is the diameter of the pipe. Of course, in our case, we also know that vi equals n sub I times d sub I, and that means that this is going to be equal to rho times n sub I di squared divided by mu. So this parameter will play a very crucial role in virtually everything in this chapter, because everything is determined by what is the dominant mode of uh, what are the dominant stresses in the reactor and what is the mechanism causing them. Now, empirically, it has been found that when, so you already can see that this is nothing but the ratio of the inertial forces to the viscous forces. Well, when are these ratios? It's obvious that when REI is small, um, you know, you basically have viscous forces dominating, and when REI is large, the inertial forces are dominating. But what is small and what is large? Well, it turns out that when REI is less than 10, right, in a system with an impeller, viscous forces dominate. Viscous forces dominate. That's it. You need not consider inertial forces. And when REI is greater than 10 to the power 4, then you can definitely say that inertial forces dominate. If you're in between, say between 10 and 10 to the power 4, so in between, you know, it's hard to say. Yeah, so this is called transition regime. What you have is a transition regime where both are significant. You can't say one is bigger than the other. Okay, so if this part is clear now, so this formula, these formulas you should remember rather than sitting and you know um, memorizing them. These will, you will see that everywhere whenever I have inertial or viscous, I always use these formulas, and the formula always comes out right. So what you need is a representative velocity, a representative diameter, and then put that velocity into rho vi squared mu times vi over di. And even if you go back and take a look at the Froude number, which was defined as the ratio of the buoyancy forces to the inertial forces, you will see that I have used the same idea. So you don't have to memorize these formulas. This thing will go through if you use it consistently throughout. Now the next thing we want to consider is uh, so now the Reynolds number will allow us to estimate, you know, um, which are the dominant forces. The next thing we want to do is we want to define uh, another dimensionless number that will allow us to estimate the power required given any Reynolds number. So, roughly speaking, um, you can see that before I get into the details, if the Reynolds number is small, the viscous forces dominate. So any power you are delivering needs to overcome the viscous forces. On the other hand, if the Reynolds number is large, you basically need to overcome the inertial forces, right? Because those are the ones that are dominant. Now, the setup here is basically going to take this simple idea into account. So, to estimate, to estimate the power required, uh, now this is actually we're going to start with again ungassed flow or ungassed flow, so no gas. And for the same reason that I gave you earlier, is the moment you start gassing, uh, these structures that form, these cavities and large gaseous structures that form behind the impeller, they really screw things up, and then you need more power. You will get less power than the impeller is actually delivering. The transfer of power from the impeller to the liquid diminishes. Now, so it is convenient. It is convenient to define so-called. This is another dimensionless number. The dimensionless. This is called the power number. And the way this is defined is, it is defined as the ratio of, this is the external force, right, that is required to overcome uh, the forces that are resisting the flow, right? So you have to move the liquid. When you try to move a liquid, it imposes resistive forces on the impeller. These resistive forces can be either inertial or viscous. But in any case, whatever they may be, your external force has to overcome these forces. So to overcome, let's just say, to overcome resistance. And this is divided by the inertial forces. So of the two forces that resist the transfer of momentum by the impeller, we are dividing it only by the inertial forces. Okay. Now, once again, we need to put some expressions here. So the first thing is how to capture the external force. Well, let's say that the power that you are delivering is P0, right? To overcome the forces that are resisting the flow. So I should point out, let me go back here. Um, I have put down two kinds of major forces. There are, to be sure, other forces like gravitation, pressure, but these forces are not that important. You know, surface forces, gravitational forces, pressure forces. You have electrical solutions, you may even have electrical forces, but for the systems we deal with, only these two forces are important. So is that part clear so far? I'm essentially, I think I'm repeating what you guys have already done. Is that part clear?
Yes,
Known to you, right? I'm asking actually, is this known
Yes,
to
sir.
you? This stuff? Uh-huh.
Yes.
So now that I've done this already, maybe somebody can take a shot at it. Uh, so if P0 is the power. Well, so first of all, in the denominator, I know what I'll have. What will I have in the denominator to describe inertial forces?
So rho vi squared di squared.
So this will be rho vi squared times di squared, where this captures the inertial stress or the stress that results from convective flows. On top, I want to capture the external force that is required to overcome them, but I want to do that in terms of power. Well, because that's what I'm ultimately after. So, what do you think I should use? Given that I have to have power there, what do I need to add to convert that into force? What manipulation should I do to convert P0 into a force? P0 is
So
the,
divide by some kind of velocity.
well, why some kind? We know what it is. So which one would it be?
By vi.
So you put a VI here. That's it. Now, this means, pull it through. So, because the reason is that power is equal to, well, maybe refresh your memory, work equals force times distance, and power equals force times, so power is work delivered per unit time. That is actually force times distance by time. So this is force times velocity. If power equals force times velocity, then force is power divided by velocity. That's why we have a P0. So this implies that force equals power divided by velocity. That's how we came to this. That means that this is equal to P naught divided by rho times VI cube DI squared. And since VI equals N sub I D sub I, then this becomes equal to P0 divided by rho. This is Ni cube Di to the power 5. These formulas are somewhat important. So the ratio of the external force that is required to overcome the resistance to the flow divided by the forces that account for the resistance to the flow due to inertial stresses is basically P0 divided by rho n sub I cube di cube. And this, keep in mind, is only being done for ungassed flows. So now that we have both the things in place, we can understand. So now, given the definitions of the Reynolds number REI and the power number, which is N sub P, so we can proceed to determine power. Well, in a way, what is the power required for a given set of circumstances? Actually, what it turns out, power, I should say, as a function of REI. So, why am I putting it down this way? Well, roughly speaking, before we even proceed, let's just start from the beginning. Uh, Supposing my Reynolds number is really, really small, then that means that the power that I need to overcome the resistance is basically driven entirely by viscous forces. Okay? So that means that the power that I need, the external force that I need over here, should be replaced basically by the force required only to overcome the viscous forces, right? Because the Reynolds number is telling me that everything is driven by the viscous forces. Conversely, If the Reynolds number is extremely high, then the numerator over here, which is the external force to overcome resistance, should be the external force required to overcome only the inertial forces. Is that part clear? Now, experimentally, it is found that if you, for a given impeller, type, so it is found, and this is going to look a lot like something you've already done. So, if you plot the power number versus the impeller Reynolds number, and this is in on a log scale. So this is basically, let's say this is 10. This is 10 to the power 2. This is 10 to the power 3. This is 10 to the power 4. And this is 10 to the power 5. And this is on a, I don't remember now whether this is the, I think that's also on a log scale. Both are on a log scale. So what you find then is that the graph kind of looks like it is linear over here up to 10, and beyond 10. So this is the, since we know up to this point you have laminar flow, and beyond this point 10 to the power 4 you have, so this is this region, you have laminar flow because the Reynolds number is less than 10. Beyond 10 to the power 4 you have turbulent flow. Now what the data shows is that the graph comes down linearly. This is a log scale, so this is also log to the base 10, and this is also log to the base 10 of the Reynolds number, and we'll understand why that is the case. And here you get a straight line, horizontal straight line, okay, and the value is given, the notation, this constant is called NP prime, and this slope we'll get to in a minute where it is going down. So we'll find out how this is happening in a minute. So on a log scale, so what we find here is that essentially over here we find NP in the is actually going as 1 over inversely proportional to the Reynolds number. So it is inversely proportional to the Reynolds number. You basically get a straight line on a log scale of slope -1. Is that part clear? I mean, if NP down here, if NP goes as 1 divided by Reynolds number, this implies that log of NP goes as minus Reynolds number I. So basically, it is this is the line of slope -1 on a log scale. Okay. So, and in between, you basically have the transition regime, and in the transition regime, you basically just join it. The graph kind of goes like this. Now we have no theory for what's happening in this intermediate regime, but we can understand very clearly what is happening in the on the left side and the right side. So let's start with the easier one. Why does NP become constant when the flow is turbulent. Can anybody see why? So first of all, is it clear that this is just like the, have you guys done these Moody charts for pipe flow?
Yes, sir. We briefly will.
It looks exactly like this, right? There is
Yes, sir.
a, uh-huh. So first of all, uh, something seems a little bit counterintuitive, right? I mean, you would expect some, if you looked at it in a superficial, intuitive way, and thought of NP as a measure of power, you would expect that the higher the Reynolds number, the higher the power you need. Am I correct? I mean, does it bother you that the graph is coming downward? Is anyone disturbed by the fact that the graph is coming downward? So anyway, um, let's just start with we have definitions of both of them. We have the definition for NP, and we have the definition for the Reynolds number, right? And I'm not talking about the detailed formulas. I'm just saying that we know that the Reynolds number is the ratio of the inertial to the viscous forces, and we also know that NP is the ratio of the external force that is required to overcome the resistance divided by the resistive inertial forces. So now, supposing the Reynolds number is really, really large, okay? So maybe I should just do this. So now, to understand this graph, let's take the two cases. The first case is
So,
going
but
to be,
ideally, if the Reynolds number
go
is
ahead.
large, then the so ideally, if the Reynolds number is large, then the denominator in the power number is large, so the power number should decrease, right? So that is what the graph shows.
If the Reynolds number is large,
So then the inertial forces would be high. So then basically the denominator in the power number would be larger, so the power number should decrease.
that might be one way to look at it. Okay, yeah, that sounds reasonable, but we'll do it a little bit more systematically. So let's say this is the laminar flow regime with the impeller power number less than, with the impeller Reynolds number less than 10. Now, since the Reynolds number is small, right? So since the Reynolds number is less than 10, viscous forces are much, much bigger than inertial forces. Okay? If the viscous forces are much, much bigger than the inertial forces, that means that the external force that you are applying needs to overcome essentially only the viscous forces. Is that correct? So, external force, which is now being applied to overcome the sum total of the viscous and inertial forces, must essentially be equal to same order of magnitude as the viscous forces, which means that NP, the power number, which was described, which was defined as this was defined as external force divided by inertial force. What will this be on the order of? This will be on the order of viscous force divided by inertial force. Is that clear so far?
Yes, sir.
But what is viscous force divided by inertial force?
So inverse of the Reynolds.
So that is nothing but 1 over the impeller Reynolds number. So this is the reason why NP is inversely proportional to the Reynolds number in the laminar flow regime. Okay. Now, if that is the case, then we basically can now expanding it. We know that NP, right, was essentially P0 divided by rho times N sub I cube di to the power 5. We derived that formula right here. We showed that NP, the definition, this is by definition of NP. So if this is essentially proportional to, if this is proportional to 1 over the Reynolds number, this is proportional to 1 over the Reynolds number. This is what we have concluded. But the Reynolds number we know is basically rho times N sub I d sub I squared. Keep in mind, this is rho Vi di, but since Vi is Ni di, you get rho Ni di squared by mu. This is what you get. But that means that P0 scales as or is proportional to, just multiply it out and you get rho times N sub I cube di to the power 5 multiplied by mu divided by rho times N sub I d sub I squared. Rho and rho cancel out, and this is of course equal to nothing but mu times N sub I squared d sub I cube. Am I connected or did I lose you?
Oh, yes, sir. Yeah.
Did I lose you for a while?
Yes, sir. There was just a second of, but it's fine now.
It's fine.
Yes, it's fine.
So basically you end up with P0 equals K times mu times Ni squared di cube. So this is the formula for where what is K? K is yeah. So K is just like, so first thing you want to notice no rho over here, only mu. Does that surprise you? Or is that obvious?
So I guess if the density is higher, then the powers needed to rotate the fluid is also higher. So
No, I don't think so. I think the reason is that basically we are talking about power compensating only for viscous forces. You have a mu here. There is no rho because we are operating in a regime where the inertial forces are irrelevant. The inertial forces are coming through the rho Vi squared term. Once you have no, in the moment you say you're operating where there are no inertial forces, rho disappears and all you're left with is mu. So that's the real reason. And so now what do you expect will happen? Do you expect rho or mu to appear? We go to the next part. So the next part is what happens in the turbulent flow regime. where the Reynolds number is bigger than 10 to the power 4, and therefore you have essentially inertial forces only. So we will go through this. This is actually much easier. What do you think P0 will have? Will it have mu or rho? Based only on what I've already told
So
you.
it should have rho because NP is constant.
And it'll have no mu because once again,
Yes, sir.
why will that happen? Well, repeat the same argument, right? So let's say the Reynolds number is bigger than 10 to the power 4. Well, if it is bigger than 10 to the power 4, then by definition of the Reynolds number, the inertial forces are far greater than the viscous forces. Well, if that is true, then the external force has to overcome only the inertial forces. That means that the external force that you're applying is of the same order as the inertial forces. Somehow inertial forces. If this is the case, then that means that NP, which was defined as external forces, the external force. So basically, whenever I use the squiggle, I mean that it is essentially proportional with some proportionality constant which is unknown. These are called scaling arguments. So the squiggle here means squiggle means scales as that is the physicists use the word scales as or proportional to. Okay. In other words, this is not a detailed derivation using partial differential equations, but the structure of the formula will be dictated. We know the structure of the formula, we don't know the constants. Now, in this case, NP, which is defined as external force divided by the inertial force, becomes essentially, right, inertial force uh, divided by inertial force. So what is that? A constant? And that constant is what we call NP prime. So you can see now that this structure of the graph is intuitively obvious now. It is a natural consequence of the manner in which we have defined NP and defined Reynolds number. In roughly speaking, at small Reynolds number, the forces are completely dominated by viscous forces. Therefore, the external forces have to compensate only for the viscous forces, which means that NP has the form viscous forces divided by inertial forces, and that's why NP is inversely proportional to the Reynolds number. But when you make the Reynolds number really high, then the forces are dominated completely by the inertial forces, as a result of which NP becomes nothing but the ratio of inertial forces divided by inertial forces, so it's essentially constant. And that constant value is NP, NP prime. Now, such a graph, this graph, it has these two properties, uh, these two parts in the laminar flow and in the turbulent flow. These are the same no matter what the impeller is, right? I mean, you can work with Rushton or any other impeller, you will get essentially the same graph. But the value of NP prime, right? This depends on So this NP prime, the value of NP prime depends on the impeller type. Okay. Similarly, if I have another impeller, right, other than the Rushton impeller, so what I might have is, for example, if I have another impeller type, I might have the graph. Say another impeller type might give me a graph that goes like this, and then like this, and then like that. So the second impeller, so this is impeller 1. This is the data, say for the Rushton impeller 1, and the blue one would be the data for impeller 2. Now they will differ with respect to these two parameters. They will differ with respect to K. The value of K will differ from one impeller to the other, and with respect to the value of NP prime. So what is K? I think K will turn out to be, so actually maybe we can just work it out in more detail. So NP goes as 1 over the Reynolds number. Let's make it more precise. Let's say this is, let's say it is equal to K times, this means that log of NP is equal to log of K minus 1 times log of REI. So this means that on this plot, K is the sort of the y-intercept of the plot. Okay, so the y-intercept changes. In the case of, in the laminar flow, the slopes are the same, but the y-intercept changes. And in the case of turbulent flow, you find that the value NP prime itself changes from one to the other. Now this is given, I believe, in these are given in the table here. So first of all, let me show you the graphs. So here, this is figure 829 of the book. Okay, and it is giving you the graphs for different geometries of the turbines. So it's turbine is another name for the impeller. So whether it is a Rushton impeller or a pitched blade impeller, the graphs change, but the structures are the same. When you put them on a log-log plot, at large Reynolds numbers, they go to a constant horizontal line, and they have a slope 1, but different y-intercepts on the laminar side. In between, you simply join them. And this is showing you the data. This is how it looks when you actually do the numbers. This is showing you the same thing for two others. So keep in mind. So this is graphical data. So this is the graphical data. This is for Rushton, right? The second one, this is figure 8.29. This is for pitched blade, right? So on and so forth. The third one is for the marine impeller. And then figure 830 is giving you this data for two more types. Say one is for anchor and 2 is for helical ribbon. These are different kinds of impellers. So for each one, the data is given. Another way to organize this data, which is analytical, is the method I just told you. I gave you the formulas for the laminar and the turbulent region, and I told you that the two types of impellers differ only with respect to the two constants, right? So that was returning to my notes. actually I used a different notation. They use the notation K1. So my notation is K1. If you use K1 here and K1 here, right, you end up with, so basically the if you know K1, you know how things change in the laminar flow regime. If you know NP prime, and you know what's happening in the turbulent regime. And in this table 8.1, they are giving you the value of K1 and NP prime for the different impellers. These two constants are enough for you to know how things behave in the laminar and in the turbulent flow regime. So it's a very simple way to apply this formula. Just take it here. But these analytical formulas, this table 8.1, this is adequate only if you are either in laminar or in turbulent, right? Because if you're in the transition regime in between, we have no formulas. Just kind of, you really need to go back to the graphs. Graphs, we have formulas for predicting what happens here and what happens here. And if stuff is happening to the left or to the right, you can simply go to table 8.1, pick up the formulas and forge ahead. So if your Reynolds number are too small or too large, no need to muck around with the graphs. You can simply use this table. But if the Reynolds number turns out to be, unfortunately, between 10 and 10,000 in the transition regime, then you have to go to the graphs to calculate the power. That part clear?
Yes, that's clear.
Okay, so I will let you know when the minor will be. It's either going to be Saturday, Sunday, or Monday, Tuesday. I'll have to figure out after looking at my timetable. And we'll skip the tutorial. So just be ready. Questions can come from anywhere, minor or the two papers that I have given. Fair enough?
Yes, sir.
Yes, sir.
Okay. All right. So I'll send a note by tomorrow, letting you know when the exam is. Okay.
Sure, sir. Thank you, sir.